So how does UART work? Whenever we have UART, there's always a start bit. So the S for start bit. The start bit is always low, okay? Stop bit is always going to be high. So what does the transmitter do? It takes parallel data, so a byte of data, and it outputs it serially. So start bit, boom, 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 stop bit. So what do you need the ready signal for? Well, outputting that data is actually going to take many clock cycles, right? How do we guarantee that we don't send data too quickly? So we use the ready to tell the logic, I'm not there yet. I cannot send the next byte of data. Please wait. So what we actually want to do is we want to check, is the data valid in this clock cycle? So what we're going to do is we're going to wait here, then we're going to wait until we're in the middle, and then we're going to sample on full periods is the gist of how the UART receiver is going to work. How do we know if the data is valid or not? Well, when we have the stop bit, let's just check what the stop bit is. So if the stop bit is a 1, if it's high, then the data is valid. If it's a 0 or low, then the data is invalid because we didn't even see a stop bit. So we might as well not decode this byte. With that information, we know that we can use the valid signal to check if our data just arrived. Right here, what we did is we had a drawing of how to use the transmitter to test the receiver. So now we're going to flip them around and use whatever we receive, we hand over to the transmitter. So what's going to happen? So valid is going to go to the enable, and then data out is going to go to data in, and D out is going to go to the board. So FTDI TX and DN is going to be FTDI RX. So there's our scope. There's Dmitry. Hi guys. That's still me. This bearded man has not changed. The blue signal is the data coming in, and then the yellow signal is the data going back out. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the transmitter takes 10 periods. The receiver takes 9.5. Whenever we have a RX and a TX, we need to buffer the data if we're sending the data straight back. So this is actually valid Verilog syntax. It's just not recommend, like no one recommends to use this syntax nowadays. But Xilinx is old school. They're OG Verilog. Here's the long pause, dramatic pause. We have it right here. So what's the actual issue? So let's take a look at it. So the issue is we get a valid from the UART before we have an enable. So the transmitter was not ready, which means that when the enable came, it was still in the last state of the transmit, which means it's not ready to send the next byte of data out. What's the solution? It's a drum roll in case it wasn't obvious. It's to add a FIFO to this. So let's add a FIFO. So basically, I'm just going to comment this back in, recompile. And then we're going to see, guys, it's not going to work. And then we'll investigate. So what's the problem? So you can see FIFO data is corrupted. The solution to this, to get it up and running in the simulator, is to implement a reset, because Xilinx does not support not implementing reset. Here we go. Here's the red board. So we want to attack it with the FPGA. All right, so it is the LPC 1343. So turns out this chip has more than one bootloader actually on it. So it has a UART bootloader. It also has a USB bootloader. Where's my infamous pointing device? I should prepare it every morning for pointing. I found it, guys. I have my pointing device. So this pin up top is gonna be our ground. This pin is gonna be 3.3. I can actually power everything off of my FPGA board. So I can power everything off of this guy. So I can take the ground connection, the brown, and I can plug it into ground, which will be the second one over. And then you can also plug in the VCC. So the trick is, once you plug it in, if the board turns on, the LEDs turn on, you're good to go. If they don't, then quickly disconnect before you fry something. So we're gonna connect them to the UART, right? So now let me get my pointing device. I lost it again, here it is. So the next two headers are going to be our TXD and our RXD. So the TX and RX of the board. So the yellow LED is actually saying not only are we in bootloader, we're in the USB bootloader. So we want to switch to the UART bootloader because that'll be easier to work with. So now if we actually take this, the other end of our pin, and if we connect it to ground, LED, the yellow LED should turn off. So I'm going to send the pin. The pin is obviously 0000. Okay, so it's not 0000. We've eliminated that one. Let's try 1111. Okay, so it's flashing red LEDs at us again. So I don't think it's 1111. Okay, so the issue is if I try to send it a pin, and it's incorrect, then it takes something like 3 or 4 seconds before it actually returns. And we want to brute force this. Do we have a reset on here? Look right here, pin 15. So what we can do now is we can type a password, try it out, hit reset, the board will reset, and then we can try again. So basically we have to implement some reset logic that reacts to a special character, okay? So why don't we decide that that character is gonna be capital R? So we wanna send a capital R from our Python script. So we'll send a capital R that'll reset the board, and then we can send our next attempt. So what are we gonna do? Well, we're gonna check, did we just receive the R's? The problem is that the microcontroller runs at 8 megahertz, the FPGA runs at 100 megahertz. And the issue that we're gonna run into is the FPGA can toggle the IO faster and the reset line faster than the board will see it. So we actually need to slow this down. So I'm shifting everything over and I'm replacing the most significant bit with a 1. If I actually receive a reset, I'm gonna change this register to be 16D0. So whenever we give it a reset, 16 clock cycles later, it stops. So whenever I get the special character, I'm gonna set RST to 1. Let's try it. So I'm gonna send a capital R. Woo! So now all we need to do is create a loop out of this. So in Python, we can just do 4 pin in range, 0, and in Python, it's always +1, so it's 0 to 10,000. Are you guys ready? Let's do this. So I had to pick a pin that is good enough where people won't guess it, but you know that it's the correct answer when it actually completes.